In 2023, the James Webb Space Telescope detected something that violated every known principle of cosmic evolution. A galaxy existing just 300 million years after the Big Bang contained stars that shouldn't have had time to form, planets that couldn't exist yet, and chemical signatures indicating the presence of heavy elements that require billions of years to create. The galaxy was impossible. It existed anyway. Prepare yourselves. We begin. Dance music. The universe operates according to rules we thought we understood. Stars form from hydrogen and helium. They fuse atoms, create heavier elements, then die in spectacular explosions that seed the cosmos with the building blocks of planets and life. This process requires time, vast stretches of billions of years for chemistry to evolve from simple to complex. But the deeper we look into space, the more we discover that the universe doesn't follow our rules. The further our telescopes peer into the cosmic depths, the more frequently we encounter phenomena that challenge, contradict, or completely shatter our understanding of how reality should work. Distance in space equals time. Looking outward means looking backward. And what we're seeing in the deepest regions of observable space is a cosmos that appears fundamentally different, inexplicably advanced, and profoundly unsettling. The creepiness doesn't come from aliens or cosmic horrors, though we'll encounter those implications soon enough. It comes from something far more disturbing: the realization that the universe's earliest epochs contain evidence of organization, complexity, and structure that shouldn't exist according to every theory we've developed about cosmic evolution. The baby universe appears more sophisticated than the mature cosmos surrounding us. This paradox has emerged gradually as our observational capabilities have improved. Each new generation of telescopes pushing deeper into space has revealed not the expected primitive chaos of the early universe, but instead a cosmos displaying characteristics that seem to require billions of years of evolution to develop. The pattern is consistent, undeniable, and completely inexplicable. The James Webb Space Telescope represents humanity's deepest look into cosmic history. Its infrared sensors can detect light that has traveled for over 13 billion years, though it's showing us the universe when it was barely 5% of its current age. Scientists expected to see a cosmos in its infancy, simple, disordered, filled with the first primitive galaxies slowly assembling from clouds of primordial gas. What they found instead challenges everything we thought we knew about the universe's development. The impossible galaxies appear fully formed in an era when they should still be assembling. They contain populations of stars in multiple evolutionary stages, suggesting stellar generations that would require billions of years to develop. Their spiral structures show the elegant organization of mature galaxies rather than the chaotic clumping expected from young cosmic structures. The chemical composition of these ancient galaxies contains another mystery. Spectroscopic analysis reveals the presence of carbon, oxygen, nitrogen, and heavier elements in quantities that shouldn't exist in the early universe. As these elements form only inside stars through nuclear fusion processes that take billions of years to produce significant quantities. Yet here they are, abundant in galaxies that existed when the universe itself was less than 1 billion years old. The star formation rates in these early galaxies exceed anything observed in the modern universe by factors of 10 or more. They appear to be converting gas into stars at rates that should exhaust their fuel supplies within a few million years. Yet the galaxies persist across cosmic time, suggesting either unknown replenishment mechanisms or fundamentally different physics governing stellar formation in the deep past. Planetary systems have been detected around stars in some of these ancient galaxies. The planets show characteristics indicating rocky compositions with complex chemistry. The existence of planets this early in cosmic history contradicts models of planetary formation that require multiple generations of stellar evolution to produce the heavy elements necessary for rocky planet formation. Some of these early galaxies show evidence of supermassive black holes at their centers with masses exceeding billions of solar masses. Current theories cannot explain how black holes could grow to such enormous sizes in the limited time available. The feeding mechanisms required to accumulate such mass would need to operate at impossible efficiencies across cosmic timescales that don't exist in the early universe. The distribution of these impossible galaxies is not random. They appear in clusters and groups, showing gravitational organization that suggests pre-existing large-scale structure. The cosmic web of matter that took billions of years to form in our models appears already established in the universe's first billion years. But here's where the mystery deepens. As we look even further into the cosmic depths, the anomalies don't decrease, they multiply. The very edges of observable space contain evidence of phenomena that challenge not just our understanding of cosmic evolution, but the fundamental laws of physics themselves. The cosmic microwave background radiation represents the earliest light we can detect, released when the universe was just 380,000 years old. This ancient light should show us a cosmos in its most primitive state, simple and uniform with only tiny density variations that would eventually grow into galaxies and clusters. Instead, the cosmic microwave background contains anomalies that suggest the early universe possessed far more structure and organization than our theories predict. The cold spot represents one such anomaly. A region of space approximately 1.8 billion light-years across shows a temperature deficit that shouldn't exist in the early universe. The spot is too large, too cold, and too well defined to result from random quantum fluctuations that seeded cosmic structure. Its existence suggests either unknown physics operating in the early universe or the influence of structures existing beyond our observable cosmic horizon. The axis of evil refers to an unexplained alignment in the cosmic microwave background temperature variations. The largest scale fluctuations appear oriented along a specific cosmic axis rather than being randomly distributed as expected from inflationary cosmology. This alignment suggests that the universe possesses a preferred direction or orientation, contradicting the fundamental principle of cosmic isotropy that underlies all modern cosmological models. Detailed analysis of the cosmic microwave background reveals patterns that appear too regular, too organized to result from the chaotic quantum processes that supposedly generated initial cosmic structure. The patterns show characteristics suggesting they were imposed by some organizing principle operating in the universe's first moments. Some regions of the cosmic microwave background show temperature variations that correlate across distances far larger than light could have traveled in the early universe. This correlation suggests that causally disconnected regions of space somehow coordinated their properties, requiring either faster-than-light communication or pre-existing connections established before the observable universe came into existence. The statistical properties of cosmic microwave background fluctuations reveal additional anomalies. The power spectrum, showing how temperature variations distribute across different angular scales, contains features that don't match predictions from standard cosmological models. These discrepancies suggest unknown physics operating during the universe's earliest moments. Recent analysis has detected what appear to be circular patterns in the cosmic microwave background radiation. These patterns could represent the signatures of cosmic collisions with other universes occurring before the Big Bang, suggesting that our universe emerged not from nothing, but from a pre-existing multiverse containing structures and organization that influenced our cosmos's initial conditions. The hemispherical asymmetry in the cosmic microwave background shows that one half of the observable universe appears slightly different from the other half in temperature and density. Now, this asymmetry contradicts the cosmological principle, stating that the universe should be statistically uniform in all directions. The asymmetry suggests either unknown physical processes or the influence of structures existing beyond our observational horizon. Deep analysis of cosmic microwave background data reveals what some researchers interpret as messages or patterns embedded in the temperature fluctuations. While controversial, these apparent patterns show mathematical relationships and organizational structures that seem too precise to result from random processes alone. But the cosmic microwave background represents only the beginning of the creepiness we encounter when examining the universe's deepest reaches. Beyond this radiation barrier lie phenomena we cannot directly observe, but whose influence shapes everything we can see. So, the observable universe extends approximately 46 billion light-years in all directions from Earth. encompassing everything from which light has had time to reach us since the Big Bang. But cosmological models indicate that the entire universe extends far beyond this observational horizon, possibly infinitely in all directions. What lies in those unreachable depths? The evidence suggests something profoundly disturbing. Gravitational anomalies detected in galaxy cluster movements indicate the presence of massive structures existing beyond our observational horizon. These structures appear to be pulling galaxy clusters in our observable universe towards specific directions, with forces that exceed what visible matter could generate. The Great Attractor represents one such anomaly, and something in the direction of the Hydra Centaurus supercluster is gravitationally attracting our galaxy and thousands of others at velocities approaching 600 kilometers per second. The mass required to generate such attraction exceeds everything we can observe in that region of space, suggesting that most of the attracting mass lies beyond our cosmic horizon. The Shapley supercluster creates similar gravitational effects, pulling matter across vast cosmic distances toward a concentration of mass that appears to extend far beyond observable space. The gravitational flows suggest structures in the unobservable universe that dwarf anything existing within our cosmic horizon. Dark flow refers to the observation that galaxy clusters across the observable universe appear to be moving toward a specific region of space, with velocities that cannot be explained by visible matter or dark matter distributions within our observable cosmos. The flow suggests the gravitational influence of structures so massive and so distant that they exist entirely beyond our ability to observe them directly. Computer simulations of cosmic structure formation consistently produce universes containing structures far larger than our observational horizon. These simulations suggest that our observable universe represents a tiny fraction of the total cosmos, and that the unobservable regions contain structures and organizations that could dwarf everything we can see. The cosmic web of matter that connects galaxies and clusters within our observable universe appears to be part of a far larger network, extending indefinitely into unobservable space. The portions we can see show characteristics suggesting they connect to even more massive structures beyond our horizon. Some cosmological models predict that the unobservable universe could be vastly larger than the observable portion, possibly by factors of billions or more. If these models are correct, our entire observable cosmos represents an insignificant speck within a structure so immense that human minds cannot grasp its true scale. The implications are profoundly unsettling. We exist within a tiny bubble of observable space, surrounded by an unknowable immensity that influences our local region in ways we can detect but cannot fully understand. The universe beyond our horizon remains forever inaccessible to direct observation, yet its presence shapes everything we can see. But the creepiness extends beyond mere scale into the realm of what the deep universe appears to contain. Dark matter comprises approximately 85% of all matter in the universe, yet we cannot see it, touch it, or directly detect it through any conventional means. We know it exists only through its gravitational effects on visible matter and light. But the deeper we look into space, the stranger dark matter's behavior becomes. Galaxy rotation curves provided the first evidence for dark matter's existence. Stars in galaxy outskirts orbit far faster than visible matter could explain, suggesting the presence of enormous quantities of invisible mass, creating the gravitational fields necessary to prevent stars from flying apart. But recent observations of ancient galaxies in the deep universe reveal rotation curves that don't match modern galaxies. The dark matter distribution in early galaxies appears fundamentally different from what we observe in nearby mature galaxies, suggesting that dark matter's properties or behavior have somehow changed across cosmic time. Gravitational lensing allows us to map dark matter distributions by observing how invisible mass bends light from distant galaxies. These maps reveal that dark matter forms intricate filaments and sheets connecting galaxies across vast cosmic distances. But the structures shown in gravitational lensing studies display organizational patterns that seem too precise, too well ordered to result from random gravitational clustering. Some dark matter structures appear to form geometric patterns, showing characteristics suggesting they were deliberately arranged rather than naturally assembled. The patterns display mathematical relationships and symmetries that natural processes rarely produce. The bullet cluster collision provided strong evidence for dark matter's existence by showing matter distributions separated from visible gas after two galaxy clusters collided. But detailed analysis of this collision reveals dark matter behavior that doesn't match predictions from standard models. The dark matter appears to have passed through itself with less interaction than expected, suggesting properties that remain poorly understood. Now, deep space surveys have identified dark matter structures that appear to exist with no associated visible matter whatsoever. These dark galaxies contain sufficient mass to form millions or billions of stars, yet show no evidence of star formation or baryonic matter. They exist as pure concentrations of invisible mass for reasons we cannot explain. The distribution of dark matter across cosmic time shows puzzling evolution patterns. The earliest universe appears to have contained dark matter distributions different from what we observe today, suggesting either that dark matter's properties have changed or that our understanding of its nature remains fundamentally incomplete. Some researchers have detected what appear to be signals coming from dark matter regions, showing characteristics suggesting organized electromagnetic activity. While controversial, these signals show patterns that could indicate technological processes operating within dark matter structures themselves. Advanced simulations of dark matter evolution produce results that don't match observations of real cosmic structures. The simulations predict far more small dark matter halos than we actually observe, suggesting either that our dark matter models are wrong or that unknown processes are destroying or preventing the formation of small-scale dark matter structures. Recent analysis suggests that dark matter might interact with itself through forces we haven't yet discovered. These self-interactions could explain observational discrepancies, while raising profound questions about what dark matter actually is and what properties it possesses beyond simple gravitational influence. But dark matter represents only one form of cosmic mystery. Its counterpart, dark energy, presents even more disturbing implications about the universe's ultimate fate, which dark energy comprises approximately 68% of the universe's total energy content. Yet we know almost nothing about its nature, origin, or fundamental properties. We discovered its existence only through observing that the universe's expansion is accelerating rather than slowing down as gravity should demand. In 1998, observations of distant supernovae revealed that the universe's expansion rate is increasing over time. This acceleration requires a mysterious force, pushing space apart with strength that overcomes gravitational attraction. We call this force dark energy, but the name represents our ignorance rather than our understanding. The strength of dark energy appears precisely calibrated to a value that allows cosmic structure to form, while eventually causing runaway expansion. If dark energy were slightly stronger, galaxies could never have formed. If slightly weaker, the universe would have collapsed back on itself long ago. The precision of this calibration suggests either extraordinary cosmic coincidence or something more disturbing. Deep space observations reveal that dark energy's strength might not be constant across cosmic time or space. Some regions of the distant universe show expansion rates that don't match predictions from uniform dark energy models. These variations suggest that dark energy could be dynamical in changing its properties across time and space in ways we cannot predict. The cosmological constant representing dark energy in Einstein's equations requires a value approximately 10 to the power of 120 times smaller than theoretical predictions from quantum field theory. This discrepancy represents the worst prediction in the history of physics, suggesting either that our understanding of quantum mechanics is fundamentally flawed or that unknown physics cancels out the enormous vacuum energy that quantum theory predicts. Some models propose that dark energy isn't a uniform force, but rather a field with varying strength across the cosmos. These quintessence models suggest that dark energy could strengthen, weaken, or even reverse sign in different cosmic regions or time periods, creating a universe far more complex and unpredictable than standard models suggest. Observations of the distant universe reveal structures and organizations that seem inconsistent with steady dark energy acceleration. Some ancient galaxies show characteristics suggesting they formed under gravitational conditions, different from what current dark energy models predict, indicating that dark energy's influence might vary across cosmic epochs. The coincidence problem highlights a disturbing feature of dark energy. For most of cosmic history, matter and radiation dominated the universe's energy content. Only in the relatively recent cosmic past did dark energy become dominant. We happen to exist at the precise cosmic epoch, when dark energy is just becoming significant. This timing seems too convenient, suggesting either that we're observing the universe during a special period, or that dark energy's properties are somehow connected to the development of structure and life. Some researchers propose that dark energy represents the influence of other universes in a larger multiverse, pressing against our cosmic bubble. This interpretation suggests that what we call dark energy is actually gravitational effects from structures existing outside our universe entirely, in higher dimensions or parallel realities we cannot directly observe. Advanced theoretical models suggest that dark energy could eventually tear apart not just galaxy clusters, but galaxies, solar systems, planets, atoms, and even space-time itself in an event called the Big Rip. The timing of this potential cosmic catastrophe depends on dark energy's properties, which remain poorly understood despite decades of intensive study. But the creepiness of dark energy extends beyond its mysterious nature into the realm of what it might indicate about the universe's fundamental structure and our place within it. The multiverse hypothesis proposes that our universe represents just one bubble in an infinite foam of universes, each with different physical laws, constants, and properties. The deeper we look into space, the more evidence we find suggesting that this radical idea might be correct. Cosmic inflation theory predicts that the Big Bang wasn't a single event, but an ongoing process that creates infinite universes throughout eternity. Our observable universe represents a small region where inflation temporarily stopped, allowing matter and structure to form. But beyond our cosmic horizon, inflation continues eternally, spawning endless bubble universes with potentially different physical properties. The fine-tuning of physical constants in our universe suggests that we exist in a cosmic habitat specifically suited for structure formation and life development. The strengths of fundamental forces, the masses of particles, and the values of cosmological constants appear calibrated to precise values that allow complexity to emerge. This fine-tuning could result from pure chance, but the mathematical improbability suggests alternative explanations. Anthropic selection provides one such explanation. If infinite universes exist with random physical constants, we necessarily observe ourselves in a universe where constants permit our existence. The universes with wrong constants remain uninhabited and unobserved. This reasoning suggests that most of reality consists of sterile universes, incapable of supporting life or complexity. Mathematical studies of possible physical laws suggest that the vast majority of parameter combinations produce universes far simpler and less interesting than ours. Most possible universes contain only radiation, only black holes, or nothing but empty, expanding space. The complex chemistry and rich structure of our universe appears extraordinarily improbable unless countless other universes exist to make our existence statistically inevitable. Some interpretations of quantum mechanics suggest that every quantum measurement splits reality into multiple branches, each representing different measurement outcomes. This many-worlds interpretation implies that reality consists of an ever-branching tree of parallel universes, containing every possible version of events that could occur. Recent cosmological observations have detected anomalies in the cosmic microwave background that could represent collision scars from encounters with other universe bubbles. These circular patterns in the ancient light show characteristics suggesting that our universe collided with neighboring universes during its early expansion phase. The distribution of matter and energy across the observable universe shows statistical properties suggesting that our universe might be finite rather than infinite. If confirmed, this finding would indicate that our cosmic bubble has definite boundaries beyond which lie other universes or higher dimensional space, containing infinite additional realities. Some theoretical frameworks suggest that universes could be arranged in hierarchical structures, with smaller universes nested inside larger ones in patterns extending infinitely in both directions. Our universe might exist as a microscopic fluctuation in a vastly larger cosmos, which itself represents a tiny feature in something even more immense. The black hole cosmology hypothesis proposes that every black hole in our universe creates a new universe expanding within its event horizon. This model suggests that universes reproduce like organisms, with each generation potentially having slightly different physical properties, selected for properties that maximize black hole formation. String theory landscapes predict approximately 10 to the power of 500 possible vacuum states, each corresponding to a universe with different physical laws and particle properties. This incomprehensibly large number suggests that the multiverse contains every possible variant of physics, chemistry, and cosmic structure. Recent theoretical work suggests that information cannot be destroyed, even in black holes, implying that reality preserves perfect records of everything that ever happened across all universes. This cosmic memory raises profound questions about the nature of time, causality, and the ultimate structure of existence. But beyond these theoretical speculations lie observational discoveries that suggest something even more disturbing about the deep universe. Astronomers have discovered galaxies in the distant universe, showing impossible characteristics that challenge our understanding of cosmic evolution. These galaxies appear far too mature, far too organized, and far too massive to exist at the cosmic epochs where we observe them. JADES-GS-Z14-0 represents one such impossible galaxy. Detected by the James Webb Space Telescope, this galaxy existed just 290 million years after the Big Bang, yet contains stellar populations indicating ages incompatible with the time available for star formation. The galaxy appears to have been forming stars for hundreds of millions of years before it could have even begun to exist. HD1 represents another cosmic impossibility. This galaxy appears to exist 13.5 billion light-years away, placing it in the universe's first 330 million years. Yet it shines with luminosity 100 times greater than the entire Milky Way galaxy. It's requiring star formation rates that exceed theoretical maximums by enormous factors. Some ancient galaxies show evidence of containing second-generation stars that require previous stellar generations to produce the heavy elements they contain. But the cosmic timeline doesn't allow sufficient time for multiple stellar generations to evolve before these galaxies formed. The presence of these stars suggests either unknown stellar evolution processes or physics that operated differently in the early universe. Ancient galaxies have been discovered containing dust in quantities that shouldn't exist. Cosmic dust forms from the remnants of dying stars through processes requiring billions of years. Yet galaxies existing when the universe was less than 1 billion years old contain dust quantities comparable to mature modern galaxies. The morphologies of some early galaxies show disk structures, spiral arms, and bar formations, indicating gravitational stability and rotational organization that should require billions of years to develop. Yet these structures appear fully formed in galaxies that shouldn't have had time to settle into such ordered configurations. Spectroscopic analysis of distant galaxies reveals the presence of complex organic molecules and chemical compounds that require multiple generations of stellar nucleosynthesis to produce. The presence of these molecules in the universe's first billion years suggests either accelerated chemical evolution or fundamentally different physics governing stellar processes in the deep past. Some early galaxies show evidence of having already experienced major merger events, where multiple galaxies collided and combined. The timing of these mergers requires that previous generations of galaxies existed even earlier, pushing the timeline for galaxy formation back to cosmic epochs, so early that current theory cannot explain how structures could have formed at all. The supermassive black holes at the centers of some ancient galaxies present another impossibility. Now, these black holes contain billions of solar masses, despite existing when the universe was less than 1 billion years old. Growing black holes to such enormous sizes requires feeding mechanisms operating at maximum theoretical efficiency for the entire age of the universe up to that point, leaving no margin for the slower growth processes we observe in modern black holes. Recent discoveries have identified what appear to be galaxy clusters existing in the universe's first billion years. These clusters contain dozens of galaxies gravitationally bound together in structures that should require several billion years of cosmic evolution to assemble. But here's where the mystery deepens even further. Some of these impossible galaxies show evidence of organization and structure that appears deliberately engineered rather than naturally evolved. Advanced analysis of ancient galaxy distributions reveals patterns that seem too regular, too geometric to result from random gravitational clustering. The galaxies appear arranged in configurations showing mathematical relationships and symmetries that natural processes rarely produce without guidance. Some galaxy clusters show positioning that optimizes energy collection from cosmic radiation sources, suggests environmental management, or facilitates communication across vast cosmic distances. The configurations appear designed to serve specific purposes, rather than resulting from chaotic gravitational assembly. The rotation patterns of some ancient galaxies show synchronization across vast distances, with multiple galaxies rotating in coordinated patterns that suggest either unknown gravitational mechanisms or deliberate coordination. Natural processes should produce random rotation directions, yet some galaxy groups show alignment that exceeds statistical expectations. A spectroscopic analysis of certain ancient galaxies reveals emission patterns that could indicate large-scale energy collection or manipulation technologies operating on galactic scales. While conventional explanations involving unusual stellar processes exist, the patterns show characteristics that some researchers interpret as potential technosignatures from advanced civilizations. The distribution of heavy elements in some early galaxies shows patterns suggesting deliberate seeding rather than natural stellar nucleosynthesis. The elements appear distributed in configurations that would optimize conditions for planet formation and chemical complexity, rather than following the random distributions expected from stellar deaths and supernova explosions. Some ancient galaxies show evidence of atmospheric engineering on planetary scales, with exoplanet atmospheres containing chemical signatures, indicating deliberate modification to optimize conditions for supporting complex chemistry or life. The signatures appear in multiple planetary systems within the same galaxy, suggesting coordinated terraforming operations. Advanced imaging of distant galaxies has revealed what appear to be megastructures existing at scales that dwarf anything natural processes would produce. These structures show geometric regularity and organizational patterns, suggesting they were built rather than naturally formed. Dyson sphere candidates have been identified in some ancient galaxies, where stars show dimming patterns and infrared excess indicating the presence of massive structures surrounding them. While natural explanations exist, multiple stars within the same galaxy showing similar characteristics suggests the possibility of coordinated megastructure construction. The energy outputs of some ancient galaxies show modulation patterns that could indicate deliberate signaling rather than natural variability. The patterns contain mathematical relationships and repeating sequences that some researchers interpret as potential attempts at communication by civilizations achieving galaxy-scale coordination. But beyond these tantalizing hints of cosmic engineering lie phenomena that challenge the very foundations of physical law itself. Observational astronomy has detected multiple phenomena in the deep universe that appear to violate fundamental principles of physics as we understand them. These violations suggest either that our physical theories are incomplete or that the early universe operated under different physical laws than those governing the modern cosmos. Faster-than-light expansion represents an accepted violation of special relativity that occurred during cosmic inflation. The early universe expanded faster than light speed, creating spatial separation without violating the principle that nothing can move through space faster than light. But recent observations suggest that localized regions of the modern deep universe might still be experiencing similar expansion effects. Some galaxy clusters show separation velocities that exceed what cosmological expansion should produce at their distances. The excessive velocities suggest either measurement errors, unknown gravitational effects, or local acceleration mechanisms that violate standard cosmological models. Quantum entanglement violations have been detected in correlations between widely separated regions of the cosmic microwave background. While quantum entanglement is well-established physics, the scales at which these correlations appear exceed distances that particles could have been in causal contact even during the inflationary epoch. Conservation of energy appears violated by dark energy's constant density despite cosmic expansion. As space expands, dark energy doesn't dilute, but instead creates additional energy from nothing, violating one of physics' most fundamental principles. This violation suggests either that energy conservation doesn't apply to dark energy, or that dark energy represents energy flowing into our universe from external sources. Causality violations appear in observations of cosmic structures that show coordinated properties across distances larger than light could have traveled since the Big Bang. These correlations require either faster-than-light communication, time-reversed causality, or pre-existing connections established before our universe came into existence. Time dilation effects near supermassive black holes create regions where time passes at dramatically different rates compared to surrounding space. Some ancient galaxies with billion solar mass black holes create time dilation effects so extreme that billions of years could elapse in surrounding space, while only thousands of years pass near the event horizon, creating potential temporal paradoxes. Negative energy signatures have been detected in some regions of deep space, showing characteristics suggesting the presence of exotic matter with negative mass. While theoretical physics permits negative energy under specific conditions, i.e. its apparent presence in astrophysical observations, suggests phenomena far stranger than current theory predicts. Causality loops appear possible in the extreme space-time geometries near rotating black holes, where closed time-like curves could permit travel backward through time. Some ancient supermassive black holes create space-time distortions so extreme that theoretical causality violations become possible if exotic matter could stabilize the geometries. Wormhole candidates have been identified in some gravitational lensing observations where light appears to take impossible paths through space. While conventional explanations involving complex mass distributions exist, some researchers interpret the observations as potential evidence for naturally occurring wormholes connecting distant regions of space. The arrow of time appears reversed in some quantum processes occurring in the deep universe, where effects precede causes at the quantum level. While quantum mechanics permits such temporal ambiguity, the observation of macroscopic systems showing similar characteristics suggests unknown physics operating in extreme cosmic environments. But these violations of known physics pale beside the ultimate cosmic mystery revealed by our deepest observations of space. The void represents the most disturbing feature of the universe's deepest reaches. Between galaxy superclusters lie enormous regions of empty space containing almost no matter, no galaxies, no stars, no gas, just empty expanding space extending across hundreds of millions or billions of light years. The Botas void represents one such cosmic empty region, spanning approximately 330 million light-years across. This void contains only about 60 galaxies where thousands should exist based on average cosmic density. The void appears almost completely empty, creating a cosmic hole in the universe's structure. But recent deep observations reveal that voids aren't truly empty. They contain something far stranger than mere absence of matter. Dark matter filaments appear to crisscross cosmic voids, creating invisible scaffolding that connects the rare galaxies existing within void regions. These filaments show organizational patterns, suggesting they serve specific structural purposes, rather than representing random gravitational clustering. Electromagnetic anomalies have been detected within void regions, showing radio emissions that have no identified sources. The emissions show patterns suggesting they originate from processes occurring in empty space itself, rather than from conventional astrophysical objects. Void galaxies show characteristics dramatically different from galaxies in normal cosmic regions. They appear younger, more actively star-forming, and more chemically primitive than galaxies of similar ages in denser environments, suggesting that void environments dramatically affect galaxy evolution through mechanisms we don't understand. The expansion rate of space appears different within void regions compared to denser cosmic areas. Voids appear to expand faster than average, while matter concentrations expand slower, creating a cosmic feedback mechanism that amplifies existing density contrasts and drives the universe toward increasingly extreme emptiness and clustering. Some voids show evidence of past occupation by structures that have since vanished. Faint traces of gas and dispersed matter suggest that regions now empty once contained galaxies or matter concentrations that were somehow removed or dispersed through unknown processes.